Okay, hi there and very welcome to everybody who's here and to our second webinar. So hosting these types of webinars is something that we want to keep on doing, providing our users with the latest in veterinary science. And for you guys who haven't seen the first webinar, it is still available to watch on our YouTube channel, which is called Sleip. Irish team vet Marcus Whale is talking about how he uses Sleip in his daily practice. And also during this webinar, you will be able to send in questions. And those questions that are more general, we will answer in text during the webinar. And if there are questions that are more related to the topic or to Elin, there will be a Q&A session in the end of the webinar. And with that said, I am very proud to present today's speaker, co-founder of Sleip, biomechanical researcher and veterinarian Elin Hernlund. Very welcome.
Thank you so much, Selma, and thanks everyone for joining in. It's great to be able to talk to you tonight about gait analysis, and I'll show you a bit of the background, both in terms of biomechanics to this application that we've created, but also a bit, the thinking that you need to adapt maybe to make full use of it in clinic practice. So I am at the university where I work, and sometimes the internet connection, even though having a cord to the Ethernet cable is not great. So I hope this will work out. If you have troubles hearing me, think that things are choppy, just give a shout in the Q&A also, so Selma or Osa can tell me that I maybe need to stop and rewind a little bit. So I'll try to get started and see if I can share my screen. So the question is, if you now see this in presenters mode, or do you see it as it should be seen? Or sorry, Selma, you have to tell me.
Yeah, yes, we can see it.
Okay, that's great. You don't have the small panel on the left side, right?
No, we can see only the presentation.
Okay, that's great. Yeah, so let's get started. This is a bit of my background. I am, as Selma said, a biomechanical researcher. I'm a veterinarian, graduated about 15 years ago. And since then, I've worked in a few different places, but most of the time I've spent at the University Teaching Hospital in Uppsala, which is the only vet school that we have. So these are some images from there and from the lab that I'm running together with my colleagues in biomechanics and orthopaedics. So you see the clinic here to the left. You see me and my colleague Emma leading a horse in the orthopedic section. We have a very nice riding arena, of course, to be able to do orthopedic exams. But all of this is actually combined with a lot of technology. So in all of these facilities, even though having equine patients around, we have a lot of technical equipment installed where we do research and clinic infusion. And that is a lot of fun. So down to the left here, you see something that we've newly built together with the Max Planck Institute. It is a 3D scanner lab for horses where we try to develop more accessible technology to be able to use in clinical practice. And down to the right, you'll see a horse that has 135 motion capture markers on it, and is doing very advanced motion in one of our motion trials. And this last image is actually some of those 3D reconstructions of motion and horse bodies that we do. So we have a super curious team of researchers that also work in the clinic, and this is really the background, and this is also sort of the birthplace of the thoughts behind Sleip. So we have we call it a locomotion laboratory, but it's actually just, a technology toys, if you like, that are placed inside this clinical veterinary environment. So at the equine hospital at SLU, the Swedish University of Agricultural Sciences, we have this technology installed. And in this case, you see just an image of one of the trot-up corridors that we have where we do orthopedic exams. And you can see that we use a very advanced motion capture system for all of our patients. where we put physical spherical reflective markers on the patients. And then there's actually a cell phone or a smartphone on a tripod in this image. And it's a little bit to show that, of course, with all this technology, this is also where we were able to validate the technology behind Sleip. So using one of these very expensive systems, and we could actually show in a publication that was published this year, beginning of this year, that Sleip has a very good precision if you compare it to this state-of-the-art system that we have in the clinic. So we've used gait analysis in this clinic, in this university teaching hospital for a long time. And it's actually been a very interesting journey because as you guys who are clinicians listening know, it is quite a challenge to give technical equipment to veterinarians. I even had, I have a veterinary research friend in Zurich, Michael Weishaupt, who I'll show you a bit of more research from later today. But he was working with an engineer who once said that he knew the perfect computer for a veterinarian. And that would be a computer that has only one button. And when you press that button, nothing happens. And, you know, I think in a way, of course, it's joking a bit about the technology skepticism that we might meet in the veterinary profession. But I really think if we go down to, you know, how the clinical situation works, we all know that having a device that you use that doesn't really work well, we don't have time for that. There is so much other things to focus on, the animals and their owners and all the, the flow of work that needs to happen around those two individuals. So technology needs to work and it needs to be simple to use. And that has really been the driver behind trying to then sort of boil down these very complicated gait analysis systems into a smartphone. So this question is one of the things we've been really thinking about. Is gait analysis useful for equine veterinarians? Because we started out being a team of researchers with a very biomechanical background, so a very researchy background. And I think the years of implementing all of these different technologies that we use at the university in clinical practice has taught us that, yes, it is really useful, but it has to be easy to use. And I think usefulness, well, of course, there is a lot of value in data and objectivity. And being a researcher at heart, you know, that's, of course, something that I strive for. But I also have a very high respect for usefulness in terms of ease of use. So we'll see if I can get you through some of that. And I think the most common argumentation, of course, talking about you know, the value of gait analysis for an equine orthopedic clinician is this. So you ask a bunch of vets who look at the same horse charting, if it's lame on the right or the left hind, or if they can just pick a limb. And there are numerous studies showing that we don't agree. And, you know, maybe that's very worrying. Maybe it's interesting. And maybe I think it also reflects some kind of truth that motion mechanics is very complicated. And understanding a painful motion pattern in a horse is not an easy task. And many times, I think when we see these studies, I've listed some of them below in the slide, that show us that if you have maybe 3 to 5 veterinarians and they look at the same horses and they're even able to do the full clinical exam, they might look at them live together or from video. Well, the results are very coherent in that we often don't agree, especially when it comes to mild or moderate lameness. So I think we can agree that data is, of course, useful to be able to address this, and also for our clients to get a very good quality exam. But it's also, I think, shows us that there is a learning curve. There is something that we can learn from each other if we think different things about a horse. And technology is not going to replace the veterinary visual assessment, but it's for sure going to be something that can maybe guide you and make you reflect a little bit more on what you do see and sort of try to interpret the pattern that you're looking at. Okay, so let's say a few words about how Sleip was developed. And well, so ease of use, you can hear that I'm very interested in that, and that is really one thing that can make gait analysis accessible for many people. The potential of ease of use for Sleip is, of course, has been brought by the development of AI technology. So what we use is something called computer vision. And computer vision is a subfield of artificial intelligence where computers, they learn to derive high-level information from images. And of course, this industry is mainly driven by automated car industries or military industries. So there's a lot of investment in this field, and it is a field that has been developing very, very quickly in the last 10 to 15 years. And interestingly, we can see that AI is actually being applied more and more for medical applications as well. And I think that's great. You know, AI should do good, and I know there's a lot of debate about that right now. But if you look out in literature and news that are coming, you can see that AI can be used, especially computer vision, can be used for disease detection in quite many fields in the human medical imaging, for example, or tissue section pathology, where you can actually find moles just from photos of your skin. And I think this is so fascinating that you can actually use an image of your skin to detect the moles that might be the ones that actually are malignant melanomas. So I think that makes you grasp a bit the potential in this technology and what it makes possible for us to do. It doesn't mean that we don't use regular or more traditional veterinary medicine diagnostics, of course, but it's a potential supplement to the diagnostics that we're already using. So what Sleip does and what these artificial intelligence or neural networks that we call them are very good at doing is recognizing objects in digital images. And also these neural networks can learn to recognize actions. So not only understanding what something is in an image, but actually what it is doing, which I think is super cool. So not only then seeing some kind of action, but actually understanding different parts of, for example, human body is something that is a very strong research field in computer vision and AI. So what we've seen being developed that is very cool is a lot of these tracking possibilities where the AI or the computer vision or neural network can detect different parts of a human body and can really understand how it is moving and extract that from just a video. And for me, being in biomechanics, and I spent so many years finding single points of motion and following those and understanding those in horses. This technology, of course, was, just super powerful in terms of how we can use gait analysis for animals in clinical practice. So what we've done is to use this technology and develop it for horses, sort of teaching a computer to understand the horse's body from a video. And we've validated that technology against state-of-the-art motion capture, which is actually what we're using, as I said, in our clinical lab or in all the orthopedic patients in the clinic, where they get these 3D spherical markers that are placed on the skin. And we could compare recording horses when they're trotting up and down using both our smartphone device and these very advanced motion technology cameras that you can see mounted here in the ceiling. We would extract motion from both of these, both from the smartphone camera, which is being processed by deep neural networks, while those physical markers are traced in 3D by a computer. And then we could compare both of these signals together to see how similar they were, so how well they sort of correlated to each other. And we could see then that the Sleip technology that we looked at, it actually had a very, very high precision, much better than I ever thought when I started this research. So in general, it's about a 2 millimeter difference between these systems when they measure, which is surprisingly good. You can look at that publication if you want. I noted it down here by Felix Järmo and colleagues. So now we'll dive more into the actual biomechanics behind what we're measuring with Sleip. And this is a bit of a long history, but this is an image from, I think, the 70s. And the guy who's standing by, it looks like a small podium, but it's a control panel. That's Ingvar Fredriksson. And he was the former professor at my department. So he was a professor of functional anatomy, and he was super interested in horse motion. And some of you might recognize his family name, because his two sons are now, well, two of the best show jumping riders in the world. So that passion for horses and the passion for motion in horses really has passed along generations. And Ingvar, he was a pioneer. He really wanted to understand how horses were moving. And already in the 60s, he started using the most advanced technology he could ever find to try to measure motion in horses. And at this time, it was super complicated. It was actually super expensive and very, very cumbersome. So for every frame of this high-speed video that is filming this horse from the side, you'd have to manually mark up each dot or each part of the body where the horse was moving to try to understand that motion. So today, it is so much easier. You could see that AI development has really boosted the possibility of what we can do in terms of gait analysis and biomechanics, because now we don't have to do like a manual manipulation of each frame, but the AI instead is learning to see the horse's body and can actually extract all of that data for us. So it's an exciting time to be a biologist when AI and computer vision technology is actually catching up so much and is making it possible for us to look at things that we could never have looked at before. Okay, so looking at lameness, Fredrik, we call Ingvar Fredriksson Fredrik, but he was super interested in measuring lameness, and he started filming horses and looking at their limb motion. The problem, though, is that lameness is not easily understood by limb motion. Instead, there were some researchers in the Netherlands in the 90s who actually found a very good model to try to understand horse lameness by doing that same type of measurements with putting these physical markers on the horse's body and filming those with a motion capture system. So what they did find was, well, don't stare blindly at the limbs. Instead, just lift your gaze a little bit and look at these upper body mass segments of the horse. And all of this has to do with the basics of the spring mass model of running. So in the upper pane here, you'll see a human running, and you'll see that I've put a sort of green dot in the well, it's not the center of mass, but in this case, it's the pelvis of the human running. And when the limb is put on the ground, you can imagine the limb being like a metal spring that can be compressed underneath the mass of the body. So when the human, I'll see if I can just point at the same time here. You don't see my pointer, right? No, okay, if I can point. Do you see it now? Okay, great. Okay, so we have the mass that we're imagining here, and we have that limb which acts like a spring. And when the mass is really compressing that spring, that's where we have the mid stance of the stride. And then when you compress your spring, you sort of bounce away off from the ground again. This is the model, the mechanical model that can be used for the running gait. And you'll see it here even more simplistic. And in a horse, of course, you don't have 2 limbs, you have 4 limbs. So in this horse that you see below, I've instead drawn 2 of these mass circles representing the mass of the body. And then you can see that the limb spring is being put on here. And then during mid-stance, that spring is being compressed. And then the horse is going to bounce up and away again. This is not the same model that you would imagine for walking. And walking is much more complicated, actually. And I think the walk is another chapter that we can talk about another time. But it doesn't have the same type of basic mechanics. And I think all of us veterinarians doing lameness exams know that the trot is really one of those really revealing gaits where you can see a very consistent, a very symmetrical pattern where you get a very, very good appreciation of the horse's lameness. The walk, though, is also giving you a lot of clinical information, but since it's not as sort of easy in its mechanics in a four-legged animal, it doesn't give us as much clinical information. So all of the biomechanical studies where we compare walk and trot in the lame horse, the trot is always very clear because it has this basic spring mass model. Okay, see if I can move along. Yeah. So what we're going to look at here is the trajectory of the upper body mass segment. So you can see that when the limb spring is being compressed, the mass segment is actually moving further down. And then when you're pushing off against the ground, you're pushing yourself upwards, forwards again. So you do that first for, of course, the left leg and then the right leg. And if you look at that trajectory, then you can see this green line here. It will actually move in a double waved pattern for each stride. So going down on the left leg, you would then move down and then push up again, and then go down on your right leg and push up again. So in one stride, that means that's a double wave. We'll try to remember that. So let's say that we're looking at a horse's head or a horse's pelvis when the horse is trotting. Then we have this double waved form. When we go down, this is the vertical displacement, let's say, of the head, and we have time here on the x-axis. And the horse will move down and impact on the left leg and then move its center of mass down. And if we're just looking at the head segment, it will sink down and then push up from the ground again, come up to a high position, a maximum position, and then go down on the right front limb and reach a minimum position. So, okay, double waveform again. We recognize that now. So what happens when a horse is lame? Well, this pattern, if you look at the head motion or the pelvis motion or the thoracic motion, if you want, this pattern will become asymmetrical. And this is really sort of the claim to fame of gait analysis as we use it today. There's, of course, a lot of other things we can look at in a lame horse, but this is the pure basics of the mechanics of the running gait. So that's why it's so important. So what you get in a lame horse is instead moving, so not compressing the limb spring as much when you move down in your left fore, and then pushing up not as much because you don't have as much energy when you are pushing up from the ground, and then instead moving down low on your right fore, and then creating a lot of force and pushing up high. So this creates a difference in these positions. And this is a bit what we'll obsess about today, because I think even though many of you have already grasped this, I think it's so good to try to really understand it. And when you look at the data from gait analysis tools such as Sleip, you should really see both this curve, how it works, and understand how that relates to the mechanics of the motion of the horse. Okay, I hope you're with me. We'll try to look at it again. So the trick here is that the force and the motion is coupled. That's why it's so important and interesting to look at this particular motion. But we'll just have a look at what happens underneath the hoof. And these are curves and images I stole from a friend, Michael Weishaupt, a professor in Zurich. So that's why his logo is up here. And you can see here that when the horse is running on this force plate, and the force plate will measure forces both in vertical direction, in sort of fore-aft, forward-backwards direction, and side-to-side direction. Then this is the type of curve we would get from such a tool. So we'll try to understand how this vertical motion really relates to the force underneath the hoof. And in light gray here, we have the vertical force. So the hoof is put on the ground, you have a bit of a peak here, and then the entire limb is being compressed, and you increase the vertical load coming up to a peak up here, and then decrease that load again. If we look at the forward backwards acceleration instead, we have a bit of a braking of the limb, so decelerating the center of mass against the ground in the sort of fore-aft direction, and then it will change direction and go up to positive, which means it's actually generating force forward instead. And this is a very important part. It doesn't look as that much force, because in trots, you know, the main force is actually between the horse and the ground in the vertical direction. So it's really one of these bouncing gaits where you're bouncing up and down. But this, of course, this forward pushing part is very mechanically important, because what does the horse want to do? Well, it bounces its way to get forward. So it's an important part, and we'll look more at that specific part when we try to understand a bit more of what Sleip is giving us as output. Okay, now we're actually moving to one of those trials. There's a lot of research that has been done on lame horses, and this is one of the experiments that we did. I think it's almost 10 years ago now. Where this is in Mike Weishauпт's lab in Zurich, where we took horses that are running on a treadmill. And as you see, this horse is running, it has a lot of stuff sticked onto the body. So it has these, again, these spherical markers that will give us 3D position of the body segments. And you'll see it has those in the face and all over the limbs and the body. But this treadmill is a very specific one. It's not your regular training treadmill, but instead it's actually equipped with force plates underneath the horse's hooves. So that means under here, this treadmill is measuring vertical forces underneath the hoof. So the first graph here that we see on top is the vertical displacement of the head segment here. And I sort of apologize for this graphical user interface. I think working with Sleip, I finally understand that graphics can be made much more beautiful and easy to understand. This is a bit more of what a researcher would do. So this is our research tool programmed by some of my colleagues. So you'll see this red line going from left to right, and that's actually sort of where we are in the video. And then there's a lot of options here. You don't have to look at those because, yeah, they're not important for this. But you'll see the lower pane we have here, you'll have these bumps of blue and, well, I don't know, is it orange something? And that's actually the vertical force underneath the right and the left front hoof. So what we can see if we look at it carefully is that you have this waveform for the head. So it does a double wave for each stride. And it actually goes down on the left, goes up from the left, goes down on the right, goes up from the right. And if you see it, there is some kind of semi-systematic asymmetry here, that one bump is bigger and the other one is smaller. And what I want you to focus on here is actually the relation between that vertical displacement of the head in this case and what happens underneath the hooves. Because if you look carefully, the force curves that show us how much vertical force there is underneath the hoof are they're actually smaller for the right front than the left front. So right is smaller, left is bigger, right is smaller and left is bigger. And that coheres very well with not going down as much with your head and not pushing up as much either. So that means if you don't create that much vertical force underneath the hoof, you don't impact the ground as much. That shows up in those upper body segments. So looking at the head or the thorax or the pelvis, you can actually see that there is less sinking and less pushing up that is related to a smaller degree of vertical force underneath the hoof. So it's actually cool that what we're doing when we're looking at these horses and measuring them in terms of gait analysis for lameness is looking at motion that is a proxy for force. Okay. So let's just look at how this would look in the Sleip application. Oh, sorry. Let's see if I can get us back. I am now stuck. Are you stuck? Let's see if I can stop sharing maybe and get back to where we should be. Sleip users, you already know this, but for the rest of you, we do show an application, a video of the horse, and of course what you did was to record with your phone a video, and that video is being processed within the tool using artificial neural networks. And what we'll look at here is a horse running, and those blue curves that you see underneath, let's see if I can again show my mouse. Do you see my mouse now? Okay, good. These blue curves, they will represent that vertical displacement of the pelvis. So you see that there's a double waveform that shows you that up and down motion of the pelvis in each stride where the application can see it. So if you look in the application at this particular view, you can actually see which strides are being measured because they are simultaneously going to be painted underneath if you see the pelvis, and on top here you'll see these lilac lines that do about the same thing, and they are actually showing us the motion of the head. And as soon as you see one of those lines being painted, then it's actually measuring that specific stride. So it's a very good way of looking at what type of data that was captured using the tool. Okay, so we'll look at the vertical displacement of the head in this case. I hope it's, I guess it's a little bit pixely, but I hope it's not that choppy for you. See? And I think even if it's choppy, I do think you'll see that this horse is lame. I'm looking at Åsa, she's nodding, and I think it's cool because Åsa, you're actually in marketing, right? So I know you know horses as well, but you're not a vet. So if Åsa can see it, I'm happy. And I think you can see that top line is very asymmetrical. So we don't have a very nice sort of similar shaped double wave, but that wave is really going down on this first part, which is the left front impacting the ground. And then when we have the right part, it's not going down as much, which means it's actually not putting that much load on, in this case, the right front leg. So this is the left on the left pane, and this is the right. Okay, that's good. I think you have got the hang of this. So now we'll instead look at a horse where we will follow both the pelvis and the head. And again, we have the same colors here, but in this case, actually Matthias at Sleip helped me to just pull out this line to actually be able to help you to follow that line visually when the horse is running. And in this case, we have a nice, a bit heavy Norwegian fjord horse as an example. So you have the blue line for the pelvis, and you have that lilac line for the head. And you will actually see those being painted on the side here, where we'll have the min happening for the left front here, and for the right front here, and for the left hind here, and the right hind here. Okay, I hope you follow. Buckle up, here we go. And again, I hope you see the horse running, that these curves are not becoming very symmetrical. And I think that goes both for the head and for the hind, but it's going to be most clear in the hind in this case. It's actually a hind leg lame horse that has a right hind limb lameness. So, yeah. I think it's beautiful that we see that this, again, these upper body mass segments, they are so important in their motion. And there is so much more you can look at. You can look at the placements of the limbs, how the horse is tracking. You can look at the flexion of the hock. You can look at how the fetlock is dropping. But in terms of measurements, there are repeated studies saying that the most sensitive measurement for lameness is these big upper body mass segments and their vertical motion. That doesn't mean that everything else that you see doesn't have importance. It's just that what you see more in the horse might give you even more specific information about what the horse is doing or where you think that lameness is located. But these upper body measurements are really telling us a lot about the forces. Okay, so again, you recognize the spring mass model and that vertical displacement. And again, just to make it really clear, we have sort of a ground reaction force. The GRF is the ground reaction force that is mirrored to this motion. So when you see the Sleip curves from now, I want you to think about that as a proxy for force. It's force distribution between left and right limb. So if we have one of these asymmetrical curves where the horse does not sink down as low on both legs, so we're going down on the left, and up from the left, going down on the right, up from the right. Do you still see my pointer? Okay, great. Then that is also reflected by a ground reaction force that is going to be asymmetrical. So that's the basics of what we're doing. And you will recognize these curves if you look at the Sleip summary. And now when you look at them, you'll not only think that this is motion, this is a double waveform where you actually have one of these curves, is each of them a stride that the horse has been taking when it's running. And you can see here that I tick the min and max box, which gives us the mean value for all of these strides, for the maximum position, the top position, and for these minimum positions. And it's these two that we do compare to each other for each stride to be able to understand if the horse is shifting weight between left and right leg. So why do we need these? In many cases, the horses are very clearly lame, or we can think that we see it. But I must say, and I think that a lot of our users that are very experienced orthopedic veterinarians can agree that there's a very high sensitivity in these measurements. So in some horses where I don't really pick up things, or I might pick up other things, these tools are so much more sensitive than the human eye to look at the specific weight shift. And it doesn't mean that the rest of the things that I see are not as important, but this I could never see as good as these measurement tools can do. And I think that's one of the good things. You have sort of a microscope of motion with you in your pocket when you're looking at horses and doing lameness exams. And then you look at all the other motion parameters as well, and they are super important. But this is an add-on to what you're doing where you get this really high precision. Okay, so now we'll move in a little bit into what happens when the horse has a difference in how high up it pushes itself, something that we often call a push-off asymmetry, or a difference in the maximum positions, or a max diff. So again, you recognize the curves, and we're in left mid stance here, we're pushing up from the left, and we're in right mid stance here, and we're pushing up from the right. And in this case, in this curve, or in this particular stride from a horse, you'll see that there is a difference in the maximum positions, also in the minimus. But you'll see with some horses, you actually have only a difference in these max positions. And I said that, okay, you go down on your limb, you compress your limb spring, and you get that minimum position. And when there's a difference in those minima, and it often goes with both a minima and a maxima, then you have a lameness. But what if you only have a push-off asymmetry? What actually happens then? And I've stolen a video from a friend's horse, so I won't say that it's lame because that would make her worried. But you can see here that in the curves that the horse has mainly a push-off asymmetry. When we look at it run, it has a saddle on, so you actually see some of the thoracal rotation that is also a bit asymmetrical due to this difference in how it's pushing. And I think we can look at this video again when it's running away from us, because you'll see in the curves, if you look at those blue curves of the pelvis, you'll actually see that this horse is pushing left from the right hind than it does when it comes off the left hind. So left hind is creating this higher position, and right hind is not pushing up as much. We're looking at the pelvis of the horse, and I think like now you can really see that when the horse is pushing from the left, it actually really rotates the pelvis in, pushes up the back, and gets this bouncy motion upwards. So it's using its left hind leg more actively than the right hind. That doesn't mean that it actually creates a difference really in how low it sinks. So it would probably take quite similar load on these limbs if we would look at that peak vertical ground reaction force. So there would not be a big peak difference in this horse. But instead, it does a bit of a different thing when it pushes up and pushes off against the ground. So sometimes we debate, is this actually lameness or is it not lameness? And I think in very many clinical cases, you'll see horses, especially if they have a clear hind leg push-off only asymmetry. So you don't see a difference in that impact phase, but you do see a difference in the push-off phase. That is often something where you can block a lameness. And I wish I could tell you that it always comes from the same spot, that we can say that it's also always a stifle problem or something like that. But that's not the case. If you think about the mechanics again, the spring mass mechanics of running, I think we have to realize that that is a very crude model of the entire motion. So that means it tells us quite a lot about the forces underneath the hoof, but it doesn't tell us enough about the specifics within what happens within that limb spring, because the limb mechanics internally between all the limb segments is actually quite complicated. So, of course, we're collecting a lot of clinical data in our databases to try to understand more about the specifics of what can be done. And I think using the Sleip technology, this will be super interesting because we can actually extract motion from a lot of different points on the horse. So hang on, hopefully we'll have something more interesting for you in the future. But we can at least say that we know that this maps well to forces, but for push-off problems, it's not the vertical forces that is the big difference. Instead, there is rather a difference in this particular horse that we're looking at now, which has a left hind asymmetry. But the one that we had before, let's see if we can look at the curves of that again. We'll go back here. We only have a difference in the push-off. And in this case, if we have this pattern, see if I can stop it here. No, sorry, I'll go back. This particular pattern that this horse has with the difference of these maxima that points out to the right. So you can see that we have the left impact here going up high from the left, and we have the right and going up not as high from the right. And then we're actually mapping this difference in this graph, and we can point it out as sort of a blob growing through the right here. And it has a value that is related to the range of motion of the entire motion of the horse. And you can see that it only has a push-off difference. And in this case, the push-off asymmetries from the hind, what has been shown in research from Bell, Kevin Keegan's group, they can see that there is rather a difference in the transition to that forward pushing force underneath the hoof. So again, I said that that little bit of forward pushing force that was not as big as the vertical force curve, it still has a lot of functional value. And that's what we see in these horses, that oftentimes they would have an earlier transition into the forward push going earlier from that vertical peak. So there is a force difference underneath the hoof here as well, but it's not really the same as in an impact lameness, where you really have a big difference in the peak vertical force underneath the hoof. So one thing that I would like to caution, though, I'll see if we can jump there. Oh, sorry. Is if you have a push-off pattern only in the front. So let's say you have a horse that has no impact difference for the front legs, but rather a push-off difference for the front legs. Then I would like to just make you cautious that that can happen in many ways. Think about the head as, of course, being a mass lump on a big lever arm, which means it can do a lot of things with the head, which is also the reason that we have quite a lot of variation in the head motion compared to the pelvis motion. But if you only have a push-up asymmetry in the front, I would like you to think about, is this actually a lameness in the leg that is not pushing up as much, which it would be for the hind. But for the front, it could rather be that it's actually the opposite lameness. It could be a neck problem. It could be a hind leg problem. So I would just like you to be cautious if you see a horse and you measure a horse and you only have a push-up asymmetry in a front leg, then no. Visually evaluate the horse again. Maybe look at the Sleip video because it plays the horse back in slow motion. So it actually gives you another visual look that can help you a lot in the analysis of that. And then, of course, there are so many other things in the clinical exam that can lead you the right way. But it's important that people are not fooled to think that that is always a very clinically relevant asymmetry. It is an asymmetry that is more difficult to interpret. Okay. So let's look again at those Sleip curves, and we'll just, in this summary view of Sleip, you'll have these curves. And in this particular case that I've taken up here, I just wanted to show you that, well, partly these asymmetries that we show that sort of grow out to the side, they're pointing to the left if they're indicating an asymmetry that normally comes from the left, or pointed to the right if it's the opposite. And they are related to the range of motion, as is stated here. So that's the entire range of this vertical motion. So you can think of it as being sort of a quotage of that motion. And that is done because we want that asymmetry to be partly related to the size of the horse. So here comes another sort of watch out when you do measurements of horses. If you then have a horse that is a very sort of a rather big horse, but it's a very small mover. So imagine that horse having a very, very small vertical displacement range of motion. Then the value that you can get from your measurements can look very big, but what you saw visually might be very small. And I think in those cases, it's just good to know. So in the Swedish horse population, we have a lot of Icelandic horses, for example, and they are quite small movers. I have an Iberic horse, a Portuguese horse. They're very nice to ride because they don't move very much vertically. I think that's why they're so comfortable to sit on. But that means you can measure some of these horses and they can actually look a little bit more asymmetrical in the measurements than they would do visually. So that's just another interpretation precaution that I want you to be aware of, that some horses that are big horses but small movers in terms of their vertical displacement, they can look a bit more asymmetrical than they would to the eye. So you always have to look at the values you get back from these measurements and think about, well, this is a measurement of the spring mass mechanics of the trot. It tells me something about how weight is distributed between the left and the right leg for both front and hind. So measuring the head for the front and the pelvis for the hind. But it is related to that size of the motion of the horse, which means that some horses can actually look very asymmetrical, but it's not a big weight shift because they're just very small movers. On the other hand, I'll show you also in this presentation a plot from my daughter's Shetland pony that she was riding for a few years. And I tried to look at the lameness in her, of course. She had a chronic lameness that was not at all big. But when I measured it, it was very, very clear. So I think in a small horse who is a small mover, those asymmetries are much more relevant. So that's sort of a take home there. Okay, so now I just want you to look at these curves and look at those sort of bars that are shown here. So now you know that's the difference between the maximus and the minimus that we're showing, and you're blobbing these out to the side. And then I just want you to move over to this overview where you do have these 4 bars. And there you have the 2 upper bars are for the front, so showing the asymmetry for that max difference for the head and the minimum difference for the head. And for the hind, we have the same thing. So that's the max difference, that's the push-off asymmetry. And then the arrow down here is the impact asymmetry. So why did we do these? Well, it has to do with being able to follow a horse over time. So if we have these patterns where you learn to look at the asymmetries of the curves and you see, okay, here's a horse that has a right front impact. And of course, the biggest asymmetry in this particular horse is a right hind, both impact and push off. Then I'm learning to take this pattern and to see that that's what's being displayed here as well. Again, I just want you to think about that this is just a mean value representation that we have to the right here, while to the left, you can still see that there's quite a lot of variation between strides. And we'll get to that as the last point I think we'll have time for today, that the variation between the strides in a run is one of those, well, maybe the most clinical significant things you have to look at. How consistent are these asymmetry patterns? So we looked at those bars, how they're made. I just want you to sort of visually be a bit accustomed to them because they are in the Sleip application being displayed here. When you have a horse and you have a lot of measurements over time, this is the small Shetland pony, and you can actually then quite easily get an overview of how this horse has been looking in the measurements over time. So when you see these bars, the 4 bars on top of each other, you know the top ones are head, the lower ones are hind, and well, indicating either impact or push off. And then you can get an easy overview of a specific individual with a lot of measurements. At the same time, it's a simplification, and that's a little bit what we're moving into here. So we'll just quickly touch upon that you need at least 20 strides for your measurements, preferably. In this case, you'll see that you have 27 steps for the front and 51 for the hind, which is quite unusual. This horse was probably tossing its head quite a lot, because otherwise normally the Sleip application would not see the hind as the horse is moving towards you, which means you get fewer hind leg steps. So if you run twice back and forth, you can see that in our instruction videos, you would normally get enough strides for a good analysis. But that's an important part to look at that analysis. So I know we're running out of time, and I think we'll continue with more webinars in the coming months. And I think we'll try to give you this information of really trying to get in-depth thoughts about what happens behind all of this data. But what I want you to see in this plot, and I think this is what we call the gait analysis plot. If you look in the bottom here, this is, you click one of those tabs and you get into this view. Then I'll just try to make you think a little bit about what this is, because again, we had the differences between the minimus and the maximus, so the impact part or the push-off part of each stride. So for each of those double waves, which is one stride, you'll get one value for the minimum difference and one value for those maximum differences. And each of those are being plotted as sort of a vector. So either if it's a pure impact, it would point, this is right front, pure impact would point this way, and then push off would point this way. So I'm going to confuse you heavily now, but these do actually have skewed coordinate systems of 45 degrees. So if you look at this impact to impact, there is an axis going here, and there is another axis going here. So one axis for push-off and one axis for impact. But each of these are pointing, if they're pointing then to the right, straight to the right, that means they both have an impact component and a push-off component. So the most typical lameness from a biomechanical perspective would both have a min-diff and a maximum difference. That means it would point straight to the right if it's the right leg problem. If it's only a push-off problem, which we saw in one of the cases we looked at today, then you would have the bars pointing, like we have in the pelvis here, pointing straight to the push-off, which means that actually these stride bars and these stride bars, they have impact either to the left and to the right. So that's very confusing. But I think the main takeaway is quite easy from these, because you can then see that the main vector we have, the yellow bar here, is actually indicating the mean value of all of these strides. And it's showing us that there is a right hind push-off problem in this particular horse. And if I can send you away with one thought about this data when you interpret, is that we know that sound horses show a lot of variability in their gait pattern. They show a lot of stride-to-stride variability. They're sort of soft. They're able to move in very variable ways. But the lamer the horse would get, the more restricted it gets in all of these body segments that have to work together to produce a trot in this case, which means they get much more systematic. So if you get a mean value of something that points out, and you had only 8 strides and they were a bit all over the map, but they were pointing maybe with a color indicating a big asymmetry to one leg, then don't put too much clinical weight into that data. You have to be very cautious when you interpret the data. You have to have enough strides, and you also have to, well, so if you move towards looking at these clock plots, I would be so happy, because you have to look at how do they, all of these strides, what do they tell you together? So if it's like a brush that is very dense and that goes particularly either straight to the right or one of these impact or push-off components here, or straight to the left or to push-off or impact, then you can be very certain that that is a very consistent weight shift in this particular horse. So consistency of data and enough strides is one of those things that is very, very important for us to say that this horse is actually shifting weight. So I think I will stop there. There is so much more to say, and I hope to be able to continue. We'll take it step by step, and I hope we have some suggestions for other webinars that we could do with other themes. I think interpreting lameness or asymmetry on the circle, for example, is one important theme. But we also know that you learn a lot from different case studies. So we'll also try to talk to you about cases, and that's actually hopefully what we'll do the next time do a bit of a case series study where you can actually look at these examples. So I think, Selma, it's time for me to try to stop talking about that.
Yeah, sorry, we actually do have a couple of questions.
Yeah, that would be great.
And can you read them, Elin? Because the first one is a bit long, so I think if you can read them, it's you see them?
Yeah, I see them. That's perfect. So Chiara is asking about the range of motion values, what they do represent and how they are expressed. Are they relative values compared to the contralateral leg? Is it possible to obtain values of diff min and diff max in millimeters like in other motion analysis systems? That's a very, very good question. Okay, so firstly, the only motion analysis system that would really give you millimeter output is that multi-camera motion capture system. That the one I use is called Qualisys. So that's the only one that gives you a really true millimeter. There are some other IMU systems that are calibrated to that system and that would give you output. I think the Equimove system, for example. The lameness locator system, which is another IMU lameness measurement system, it also gives you a relative asymmetry to the range of motion. So it does about the same thing. Let's see if we can go back to one of those curves looking at the range of motion representation, or sorry, these asymmetry bars. There we go. Okay, so in this case, for example, so if you have these bars, we'll take one with where the values are there. Yeah, so these bars are the differences between the minimus and the maximus, but they're related to that range of motion. And the more complicated answer is actually that it's not only that vertical range of motion, but we're actually doing a signal decomposition of this motion that the horse is doing, where we're looking at the symmetrical component of it. So it's a frequency decomposition of the signal, where we're looking at, well, it is technically a bit more complicated than what I'm saying, but it's more or less the symmetrical part of the component of that signal or the motion that the horse is doing. So what you're seeing here is not the output of the range of motion, it is the asymmetry related to the range of motion of this particular horse. I don't know, Chiara, if that answered your question. I'm happy to send you an email about it if you want also. You can email me. But the lameness locator does about the same thing that we are doing here, and other systems would rather give you the actual millimeter output, like the Qualisys system, for example, because they actually measure in millimeters with a very high precision.
Okay, and I think Åsa answered. Oh, here's one question. Oh, two questions. Okay, let's go. Sleip can identify a problem when a horse is moving symmetrically, but with very short moves according with the breed.
Okay, yeah, that's a great question. I think we all see a lot of choppy horses where you think, oh, is this a bilateral lameness? Is this a poor motion pattern, if I'm blunt. And of course, the horse, when we do this type of measurement and the horse is moving on a straight line, the horse would have to be asymmetrical between the left and right to give this type of asymmetry value. If the horse is actually bilaterally lame, of course, we would probably see that on the circle in most cases when we compare the left and the right circle. And then the horse would become unexpectedly asymmetrical on the circle instead, which can be measured, of course. We will, when it comes to like a high frequent motion or this choppy type way of moving, that is of course something that we know from biomechanical studies that's a strategy for the horse when it becomes lame, to run with shorter and more high frequent strides. So let's say a horse has a very, very small lameness or it has a bilateral lameness. One of the strategies, of course, would also be to run slower with more high frequent strides and shorter strides. That's a way of sharing the force between the legs and between more strides, so to say. So I so often call that sort of impulse sharing. So sharing the impulse would be the force over time under each hoof. So what we'll do is we'll soon give you, or we're developing more values for you to look at that I think, might not be valuable for all cases, but in some cases, especially if you follow an individual horse over time, looking at the stride frequency, for example. So that will eventually be one of the things we're displaying as additional information for you. Of course, you have to know that if you measure stride frequency, it has a lot to do with how fast you run with the horse, but it's still something that we see when we analyze all of our clinical data from the university clinics that we're working together with data analysis of their clinical cases. We can see that, of course, horses, when we block them, so they're lame initially and we block them, they do move with longer and some sort of more low frequent strides. And I think you see that as a clinician really well as well. The horse is all of a sudden more comfortable, it takes longer strides, it has more of a relaxed motion. But it is difficult because it's not, in terms of gait analysis and this spring mass model of running, it's asymmetries that we focus on, where we can really say that there is a weight shift between the left and the right leg.
Thank you. And there's one more question. I think you can just answer that one, and it's from Patrick. It would be interesting to understand the importance of a flat surface or the differences between hard and soft footings. My apologies if this was covered before I joined. No worries.
No, Patrick, that's great. I did not cover that. Of course, the surface would have an impact on the lameness in many horses. When it comes to if the surface is flat or not, of course, the horse would move with more variation or more variability if the surface is bumpy. What you should watch out for, and that's really important, is that you don't measure on surfaces that have a very clear side to side slope, because there are several studies showing that if you would increase the height of one leg of the horse, then of course that would create an asymmetrical motion pattern. So that means if you measure it, especially for the pelvis, because we only see that when the horse is moving away, if you have a surface that is really sort of side sloping, that would make one leg longer and the other one shorter, more or less, when the horse is running, and that would create an asymmetry. So that you have to take into account. Otherwise, that sort of bumpy surface, of course, in my clinical opinion, if it's slippery or if it's bumpy, the horse would stiffen up and not move its center of mass as freely as it would if the surface was comfortable and had a good grip. But otherwise, the measurements are actually really good at sort of distilling out asymmetry that is important anyways, as long as you can collect enough strides. So I think even if you're in this field setting and you have a gravel road and it's not the most perfect gravel road, I think it's often, it gives you a lot of information still to use that surface, and you can often see lamenesses and you can get helped even more, I think, sometimes with these measurements in a setting like that.
Thank you. Actually, we should end up, but this is a very interesting question coming in right now. Do you have time yet into I just answer?
Yeah, sure.
So it's a quite long one. Do you want to read it yourself? Or
yeah, I can read it out. This is a farrier writing a question. Who works with a couple of different veterinarians. The work I do with the two veterinary clinics is mostly focused on lameness issues. I'm also consulting with a different veterinarian specifically on performance. What experiences have you seen for farriers and veterinarians working on lameness issues to adjust trimming and shoeing protocol to support the horse? Obviously, the farrier isn't involved in many of the lameness issues. How about the performance side with vets, farriers, and trainings working together using Sleip? Yeah, what a great idea. We do have the same idea, Wayne, of course. And I think one of the passions that really unite us at Sleip is the use of data for a lot of the assessments that are done of a horse in any situation. And that would be, of course, also before and after it's being shod, and especially creating a network of professionals around a horse when it comes to optimizing performance, but of course also optimizing the health of the horses. And we know that shoeing is so important for the longevity of the horse and the performance of the horse. So today we don't have a tool for farriers. We do have a few farriers that are allowed together with some veterinarians to use the application. And what we're hoping to do is to create a communication tool with these objective data and videos that can be used by the professional team surrounding the horse. We're not there yet. Now we're working with the veterinary application. And of course, measuring lameness is something that a veterinarian should do. And that's why we also think these webinars are really important, because we want the veterinary community to be specialized in understanding these types of measurements so that they can really be sort of the mothership receiving all this information in that can be interpreted, and as you know, how you should interpret that in terms of health issues around the horse. But we would love to create a network and tools that can be used both by farriers and by physiotherapists that can work together with the veterinarian. And with the Sleip technology, you can share data more easily. And what we've done now, we're testing to use the application between a horse owner and the veterinarian during the phase of rehabilitation of a horse, where the veterinarian actually invites the horse owner to record data at home between the visits. And that, of course, is something that would be very suitable to do in one of those well-functioning units of farriers and veterinarians, or veterinarians and physios as well. So we're really passionate about how this can lead to improvements and where you can get these sort of actionable insights between these professional groups working around the horse, where we can pick up things in the right time and we can actually evaluate better how, for example, therapeutic shoeing works in a rehabilitation phase for a horse. And Wayne, I think often, like, I'm a vet and I treat horses, but I often think that you farriers can make that real big change in some of these orthopedic cases that make the horses sound more permanently than I would do with my injections. So I think it's super important that we would do that work better together, and that we get ways to communicate around the data and video of horses to be able to do a better job together.
Okay, thank you so much, Elin. We're running out of time here. But we are super happy that you all have joined us here tonight, and it's time to wrap it up. And if you are curious on our product and would like a demonstration, please go to our website and click on the book a demo button. And I think that's it for tonight, and hope to see you in our next webinar in June.
Yeah, and can I just maybe make some publicity? I think we were having one of our biomechanics PhDs and experts, Asha Hardeman, who has worked at the Visha Clinic for many years, and she will host the coming webinar. So don't miss that. She is really great.
Maybe you should start working in marketing instead, Elin.
Oh, yeah, who knows?
Yeah. So thank you so much for tonight, guys, and have a nice evening. Bye.
Bye-bye.